Hi, I'm Giorgio Letizio from the University of Trento, and today I will present a calculus of tracking, theory and practice. When we browse the web, we are now get used to the presence of cookies and of the tracking techniques that are associated with them. As the techniques becomes more and more invasive, a set of tracker blocking tools has been proposed and are now widely employed. And this also brings the attention to the researcher that try to analyze them and see which are their performance. But most of the state-of-the-art works that aim at measuring trackers and evaluate tracker blocking tools are based on large-scale analysis, in which a browser contacts several thousand or million of domains with a certain extension installed to determine which one perform better. From this experimental study, it's not uncommon to observe contradictory results due to, for example, different settings. And these results often lack transparency. And in this case, there's hardly any way for a third party to check this conclusion unless one rerun the entire study. Furthermore, does a user really need to know that a certain tracking blocking tool outperforms another by visiting 1 million of domains? Or should it be more interested in evaluating the efficacy in few domains he usually visits? One can think that in case of few domains, a manual inspection can be a solution. However, analyzing the web tracking activity, even for few domains, is now impractical due to the high complexity of the web interaction. So we presented a framework for the analysis of web tracking that provide an independent verification of tracking practice by websites. And the framework is based on the most known tracking techniques and data exchange that are performed by trackers. And all these tracking techniques are observable from the client side. We model the tracking practices via formal rules based on intuition first order logic. And our framework is able to automatically instantiate the rules based on snapshot of the internet that one can obtain from Clojure like OpenWPN. In our framework, we also take into account the non-determinism of the web interaction. So for example, when we visit a website multiple times, it happens that we include and load content from different resources in each visit. And we thus consider also the probability of observing different trackers while visiting the website multiple times. We then applied this framework to analyze the trade-off of tracker blocking extension to help users determine the performance for their own needs. And we then also use the framework to determine potential need for compliance for the Children's Online Privacy Protection Rule that, similar to the GDPR, imposes requirements for websites that collect personally identifiable information from children. To determine tracking practice, the framework employs a formal model that describes different tracking techniques like third-party tracking, cookie syncing, and so on, by the composition of different rules that describe steps in the tracking procedure that are typically performed via network interaction among websites and between a website and the user. The rule presents some preconditions that must be satisfied and must be observed from the client side. And if all these are satisfied, the rule generates a postcondition. The postcondition can be used by other rules, so to compose a sequence of rules to describe a certain tracking practice. And the tracking blocking tools are also included in the model as additional precondition. And this allows to disable specific steps of the tracking. We focus the analysis on the most common defensive approaches employed by this tool. And thus we model tools that either do not allow the domain to store cookies on the user browser, or that directly block the connection to the domain. So let's now see an example of a common scenario that can happen in the web, in which a website includes content from a third party. And this third party is thus able to know that a user visited the primary website. And we will map this technique to a sequence of predicates and rules in our model. So first of all, we have site.com that includes content from tracker.com, and this is described with the include content predicate. This directly maps to a potential link between site.com and tracker.com that can be used for an exchange of information. Now, suppose a user visits site.com. This is described obviously with a predicate visit site.com. It will start interact with both the content of site.com, but also the content that is included from, for example, tracker.com. Now, the browser can present some extension that try to protect the privacy of the user. And this protection can try to avoid to establish a connection to a known tracker. But if this tracker.com is not included in the filter list of this extension, then the user will load the content from tracker.com. So we'll start interacting with it. And this will mean that we'll access from sign.com the content from tracker.com. Other extension can try to prevent a tracker to store cookies on the browser. But if, again, the tracker.com is not included in the filter list, it will be able to send a cookie to the user and will remember that this user has visited site.com. And this is described with a final predicate. This is in the knows predicate. They say that tracker.com knows that the user visited site.com. The example of the previous slides is obtained from the instantiation of different rules that are composed together to describe a certain tracking technique. In this particular case, we apply the inclusion rule that generalizes the presence of inclusion of content from a website to another. Other rules can, for example, model redirection that are still used for tracking practice. Another rules is the access rules that produce a potential connection that can be, for example, established through an inclusion or a redirection to a real connection. In the case, the tracking blocking tool does not present and does not consider the website in its filter list. And finally, the third-party tracking rules that, as we can see, use as precondition the postcondition of the access rule that describes the final procedure in which we have a user that visits a website and is forced to contact a third party from the primary website that will eventually store a cookie and will thus know about the visit on the primary website. So our framework allows to analyze tracking practice based on internet snapshot. And these can be obtained from the rich set of database available from tools like OpenWPN that can crawl the web. The framework is able to automatically instantiate the ground predicates that compose the precondition of the rules, and then derive all the remaining predicates to determine the presence of tracking practices. We analyze the complexity of web interaction and how this maps to our model with a snapshot of the internet that collected the HTTP responser for few top Alexa domains. So for example, by visiting only the top 10 Alexa domain, the framework detected roughly 1,000 connections, of which 800 are inclusion that will be mapped to the inclusion content predicates, and roughly 100 are redirection that will be mapped to the direct domain. From this, the framework will generate the link predicate, and from this will then propagate to all the other rules to determine tracking practices. The predicate derived from the rules are then used to evaluate the trade-off of different tracker blocking tools. So we use the number of unique instantiated knows predicate to measure the number of potential tracker a user can encounter while browsing the web, while we use the number of unique access predicate to describe the connection established while browsing the web. And this is used to measure the potential site breakage of different tools. From these predicates, we can then determine if a tool is better than another by comparing these two values. The tool A is better than B if it allows more connection, and this is observable via the number of unique access predicate observed from the two tools, but it keeps a lower number of trackers, and this is observable by the number of unique knows predicate. We compared the performance with the predicates we showed before for different tracking blocking tools by analyzing the fraction of allowed connection and allowed trackers with and without the extension for different set of top Alexa domains that can be visited by a user. The two lines in the graph show two different efficiency levels that tracker blocking tools can achieve. The one-for-one define a tool that, by allowing 50% of the total number of possible connections, it allows 50% of the overall observer tracker, while the one-for-two describes a tool that, by allowing 50% of the connection, allow only 25% of the overall tracker. That is more efficient. We can clearly see that given the same number of top Alexa visited domain, the different tools provide either more privacy at the cost of less connection, and thus a potential higher breakage, or less privacy, but a higher fraction of allowed connection. If we take the example of EasyList and EasyPrivacy, by visiting the top 5 Alexa domain, the tool allows only 20% of the connection and a little more of 20% of the tracker. The performance, instead, by visiting the top 10 Alexa, follows the one-for-one efficiency line, in which by allowing 10% of the connection, only 10% of the tracker are observed. Instead, if we then move to visiting the top 50 and top 100 domains, the tool improves its performance by reducing the number of allowed trackers, but increasing the overall number of connections. The second application of the framework is to determine potential need of compliance for the COPPA policy. And to do that, the rules are encoded in a theorem prover, in which we can ask to find a proof that shows if a certain website should or not require to comply with COPPA. This is because, for example, it collects or it allows third party to collect information from children. And the tool will produce a proof, if this exists, based on a snapshot of the internet that we provide in input to the prover. The tool will search in parallel from all the instantiated ground predicate from the internet snapshot and will output a combination of the rule as a proof. So by following the previous example of site.com and tracker.com, the prover will find and include content from site.com and tracker.com. It will then derive a link between site.com and tracker.com. If there's no any tool that block the request to tracker.com, and this will be the case, it means that there's an access by the user from site.com to tracker.com. If the user that, for example, is a child visits site.com and there's no extension that blocks cookies to be stored on the browser, it will produce a knows predicate. They say that tracker.com knows about the visit to site.com of the children. Now, suppose this site.com is a website directed to children. This means that site.com should comply with COPPA. And this proof is obtained by the application of some web tracking rule that describe, in this case, the third-party tracking, and some COPPA rules that describe that if a site is directed to children and allows a third party to collect TAA, then site.com must comply to COPPA. So we presented a framework for the analysis of web tracking practices that fill the gap between large-scale studies and manual inspection by providing an explanation in the form of a proof. And we show that the framework can directly analyze data from different internet snapshots to evaluate trade-off of tracker blocking tools based on the predicate obtained from the rules, or also to determine potential need for compliance with the COPPA policy. Future direction can try to extend the model to consider additional tracking techniques like browser fingerprinting and associated blocking tools, like the ability to disable tracking scripts. This will require to investigate also possible back-off data sharing of these identifiers, and also this will have an impact on the tractability of the formal analysis.